Welcome class to our Unit 2B video notes section on Skill 5, which is going to be on writing equations of polynomial functions. In some cases, you'll be given roots, and from that, you'll have to create the equation. And then in the other case, you will be given a graph, and then from that, have to write the equation. So the things that we will basically be doing will be converting our roots, which is another word for zeros. We're going to convert those back into factors, and then we are going to basically write our equation as a product of factors. So we'll have to keep a couple things in mind when we do that, and one of them is that we need to make sure we don't have any fractions in our final factors when we're writing our equation, because if you notice, the equations that we start with never have the fractions in them. They just create zeros that are fractions. And so we'll have to kind of work backwards to get rid of the fractions. And basically that'll just come out by multiplying by a denominator. And I'll make sure I make a point of when I get to that step so you know what that's referring to. Any roots that happen to be irrational or complex will have, first of all, we have to understand that they come in pairs because they come from quadratic factors. So we're going to have to make a note of that. And so anytime we have a irrational, which is something that's like a square root of a non-perfect square, like square root of 5, or a complex root, that would be anything that has an I in it, like I square root 5. Those came from quadratic factors because they came from having square rooted two sides of an equation. So they also come in pairs because they always come in like plus or minus square root pairs. So we will have to kind of make a note of that and multiply those back together to make sure that we created a quadratic factor. And then basically once we write that equation as a product of factors, you're done. I am going to show you though how to distribute from there to get it into standard form, but that will be optional, not something that I will require of you on a test or quiz. So let's start down here with example 1. I decided to start with something that just had two single factors that are both rational, just so you can kind of get an idea of just converting back from the root back to the factor. So what we have to understand is that these numbers 3 and -4, these are the roots, okay? And root is another word for 0. So that means these are the values that we got for x when we had something that was set equal to 0. So these are solutions. So we're starting with the solutions, and from there we're going to go backwards to what must have been the factor that was set equal to 0. We're kind of working backwards. So in this case, to get 0 on this side, I'm just going to subtract 3 over. And so what that tells me is that if I have a 0 of 3, I must have had a factor of x minus 3. And over here, to go backwards and sort of unsolve for x, which is kind of weird, but this is just for you to see how we go from having a 0 or a root of -4 to a factor of x plus 4 is we sort of work backwards, we unsolve. So I know that x minus 3 and x plus 4 must have been the factors of this quadratic equation. I also know it must have been quadratic because if it has two zeros, then it must have a degree of 2, right? We also know that as well. Okay, so then for your equation, you just write y equals, right? Y, because you're writing the equation of a function, so you need your output variable also. So y equals the factor of x minus 3 times the factor of x plus 4. And honestly, on a test or quiz, I'm fine if you just write your answer like this, you could be done. This is intercept form or factored form, perfectly acceptable form of a quadratic. So this is the equation. You just literally write it as a product of the two factors that must have been set equal to 0 to create these roots or zeros. Now, for the sake of just learning and seeing connections, I'm going to go ahead and FOIL this out so you can also see what the standard form equation would be. So if I FOIL it out, x times x would give me x squared, x times 4, 4x, -3 times x minus 3x, -3 times 4 minus 12. I'll go ahead and combine those two middle terms because they are like terms. So that just creates 1x. 4 minus 3 is 1x. And then minus 12. So this here, you can see it's quadratic, right? It's got that degree of 2. It's in the standard form, right? ax squared plus bx plus c. And so this is the standard form equation, right? Because that's what was mentioned here. If you want to write it in standard form, you're going to have to go ahead and multiply. Distribute is kind of how we multiply when we have polynomials, so it's another word for multiply. But basically, that's what you do to go from the factored form into standard form, is you just multiply them out. And it's not required, it's optional. But I wanted you to kind of see the connection between the roots we were given, the intercept form of the equation, and the standard form. Okay, so let's go to something a little more complicated over here with example 2. Now I have 3 zeros, -7, 5 halves, and 0. So I know my degree for this is 3. I'm going to end up with a cubic equation when I'm done. One of my zeros is a fraction, so you're going to see we're going to have to do a couple things there to get x by itself. So I'm going to start by having my solutions written out here, right? Because that's what these values were. These were values I got for x when I started with some factor set equal to 0. So that's kind of what we're looking for. This one's already set equal to 0, so that's my factor, right? My factor must have been x. That created a 0 of 0 because x set equal to 0 creates a solution of x equals 0. So basically that's the factor. But these I'll have to kind of work backwards a little bit. And so I get a factor of x plus 7. So a factor of x plus 7 creates a root of -7. So this one here is going to refer back to this step here. I have to start by multiplying by the denominator for this specific factor, right? Only this one factor do we multiply by the denominator. And then so then I get here, I get 2x was equal to 5, a single number, and then I can subtract that 5 over, and then I can see, okay, this must have been the factor that was set equal to 0 to create a root of 5 halves, because I must have had to add 5 over to get 2x equals 5, and then divide 2 over to get 5 halves. So that creates my factor of 2x minus 5. So my three factors are x plus 7, 2x minus 5, and x. And so we're going to go ahead and write our equation as a product of those factors, right? Write the equation as the product of the factors. And it's not wrong or more right to write x first. It just looks better to have, if you have a single factor like this, just x by itself, it's nicer to kind of write that in front. So x times x plus 7 times 2x minus 5. So there is our equation in intercept form, which again, on a test or quiz is more than acceptable. If you can do this, you're amazing. For the sake of the video, though, I will go ahead and FOIL it out just so you can see the connection between these zeros and the standard form. So I think what I'll do first is distribute the x to the x plus 7. So I'd get x squared plus 7x. And then I'll FOIL that factor, x squared plus 7x, to the 2x minus 5. And so when I do that, I get 2x cubed, because I have x squared times x, minus 5x squared, plus, if I do 7x times 2x, I get 14x squared, and then 7x times -5 is -35x, and then I can combine these two in the middle. Let me kind of go down here like this, and then my final answer would be, in standard form, would be y equals 2x cubed plus 9x squared minus 35x. And that would be our final answer in standard form. So one connection I wanted to make is that if you do have a root of 0, that could only happen if every single term in your equation has an x in it. Right? If you have an equation where every single term has an x, that must have meant there's a GCF of at least one x, right? You can kind of see that here. And then that's how we end up with a factor of 0. It's just nice to see those little connections. Moving on to example 3. This one gets harder still because now I have these two roots, which look like factors, by the way. These are not, but these are numbers. These don't have any variables in them. Remember, I is the imaginary number that stands for the square root of -1. So these are what we call complex roots, okay? They are a combination of a real number plus an imaginary number, so it counts as a complex number. And notice how they have come in conjugate pairs, or a conjugate pair, right? It's same numbers, 5 and 2i, 5 and 2i, opposite signs. This means that they came from having solved a quadratic factor. So that's what I'm looking for here, is a quadratic factor. So I want to show you something. I'm going to show you this one time in example 3, but it pertains anytime you have roots that are either complex like these with I, or irrational, meaning they would have square roots of non-perfect squares. So first of all, I know that both of these are solutions to having set a quadratic factor equal to 0. And then when I did that, these were what resulted for x. So this was kind of like the end of an equation, right? X equals 5 plus 2i, x equals 5 minus 2i. I know that somewhere before all that, I'm going to kind of backtrack. It must have been because I had something set equal to 0 that resulted in these solutions. So I'm going to unsolve for x. I'm going to start by subtracting that real number part to the other side. I'm going to show you with both of these at the same time, because actually what I really want to show you is you only need to do this with one of them. And you're about to see why in just a moment. Because these both are roots, right? But they have come from the same quadratic factor. And you'll kind of see that as I go backwards. So you only need to take one of them and do this process. And I want to show you by showing you both and showing you that it produces the same thing. Now remember, when we start with a quadratic factor, it doesn't have I in it. It only has rational numbers in it. So what I'm going to do with both of these is I am going to square both sides, right? Square both sides. The reason for that is because 1, I know that I'm looking for a quadratic factor, but 2, because then that will turn this imaginary number into a rational number, because I squared by definition is -1. -1 is a rational number. So then what I'm going to end up with is x minus 5 times x minus 5 equals, and then 2 squared is 4, and I squared is -1. So that's what I end up over here. And then look, that's the same thing I would end up with over here. I'd have 2 factors of x minus 5 that I need to multiply together, and then I'd have -4 squared, -2 squared, which is also 4, right? -2 times -2 is 4, and then I squared, which is -1. These are the same, which means I don't have to do this 2 times. I just need to do it the 1 time. And look here, as soon as I FOIL this out, it will be the quadratic factor that I'm looking for. So that's what I'll do next. I'll go ahead and FOIL this out. X times x, x squared, x times -5, -5x, -5 times x, -5x, -5 times -5 is +25, and then all of that equals -4. So the last thing I would need to do is just move the -4 over, and voila, I'm at the part where I have a quadratic factor set equal to 0. Pretty fancy, huh? It's kind of cool if you think about it, that we can unsolve. We can take these roots, backtrack to figure out what was the equation that produced those roots. That's a pretty amazing skill. So actually, this is our quadratic factor right here. And since the equation I was looking for was a quadratic equation, I have actually found my equation as well. That was my equation, right? If you graph this on Desmos, you'll notice it doesn't hit the x-axis ever. It doesn't have any x-intercepts because both of the solutions were imaginary. And so there's our answer for number 3. Now number 4, let's see, let me carve out some space for number 4, is a little bit more complicated. Well, it is and it isn't. It is because it has both a rational root and a complex root, and because it has a third root that it's not showing us here, right? Because we have to know anytime you have a complex root, it must have come from square rooting a negative, which could only have come from a quadratic factor. And whenever you square root something, there should be a positive and a negative root. Complex roots always come in conjugate pairs, but sometimes they're not listed together because the assumption is that you know they're both there. Kind of a messed up assumption if you ask me, but I'm doing this to you to prepare you for other standardized tests and things that are out there. They're going to want to be checking to see that you know that. So even though negative 8i wasn't listed as a root, it has to be a root if positive 8i is. And let me kind of show you why. Let's start by just saying, okay, x equals 8i must have been the solution to some factor set equal to 0, okay? So I need to go backwards and figure out what that factor was. And I know that that factor couldn't have had any i's in it because all these polynomial equations we've been working with never have imaginary coefficients, only real number coefficients. So never have any i's. So then I'm going to have to square both sides in order to make sure that happens. So then I have x squared on the left side, 8 squared, which is 64, times I squared, which is negative 1 on the right, okay? So I get x squared equals negative 64, and then all I would have to do is add that 64 back to the other side to have my original equation set equal to 0. Okay, so what I just found out is that if x equals 8i is a solution to a factor being set equal to 0, if it's a root, that factor that it came from must have been quadratic, right? X squared plus 64. So now I am going to go back the other way, right? I worked my way backwards to get the factor. Now let's see what happens if I take that factor and solve for x. Now I'm going to go forward, if you will. I'm going to subtract the 64 back to the other side, okay? And then I'm going to square root, right? That's the opposite of squaring. I'm going to square root. So remember, whenever you square root two sides of an equation, the other side you have to write plus or minus 8i. So both of these roots, positive and negative 8i, come from this one quadratic factor. So even though negative 8i wasn't listed as a root, it has to be if positive 8i is a root, because positive 8i comes from this quadratic factor, and so does negative 8i. Anyway, long story short, x squared plus 64 is one factor. The other factor comes from the 0 of 3, the root of 3. So if there's a root of 3, then there must be a factor, right, of x minus 3. So this particular polynomial had two factors, but one of them was quadratic. So here's our equation. Here's our answer. Our answer would be y equals x squared plus 64 times x minus 3. So that'll be our final answer. And I'm just going to stop there because we've already done a lot of work to get to this point. And so that's pretty good. But I do want to point out one thing, and that is that the degree of this would in fact be 3, because I've got x squared and x. So if I were to FOIL it out, I'd have to multiply those together. And at some point, I'd have a term with the highest power of 3. That's another indication that there should be 3 roots, not just 2. 3, 8i, and negative 8i. Moving on to examples 5 and 6. These examples are wanting us to write a possible equation that could create the graphs that we see here. And we know that they're going to have to be polynomial equations to have these graphs that kind of have turning points in the middle and then point off into these different infinite directions. These are the features of polynomial functions, and we're going to try to write equations, possible equations that could create these graphs. The reason I'm saying possible is because there's going to be no way for us to know for sure if this has any complex zeros, because only real zeros show up on a graph as x-intercepts. So if this graph came from an equation that has complex zeros, there will be no way for us to know. So we're only going to be able to use the real zeros. But you'll see by checking on Desmos that that's actually, that can still actually give us a pretty decent possible equation just from using the real zeros. Now there is one extra thing that we will be able to use with graphs that we weren't able to use when given the zeros, and that is the y-intercept. By drawing upon the y-intercept, we will actually be able to figure out our a value instead of just assuming that it equals 1. And actually, that's a quick side note. let's go back really quick. For all of these equations that I wrote back in examples 1, 2, 3, and 4, in every single one of them, we were just assuming that the a value was 1. And the reason for that is, if you'll notice, I just have a 1 in front of all of these. Well, actually, this one was 2, so never mind. We didn't assume that for example 2, because it actually came out to be 2. We were able to figure that out from the x-intercept. But for the rest of these, there were 1s in front, and we were just sort of assuming that. We were just assuming that a was equal to 1. So that's our limitation when we're writing the equation given roots. But when we're given a graph, we can actually figure out what a will be by looking at the y-intercept. So that'll actually be something extra that we have with graphs that we didn't have with equations. So let's get started. So with number 5, the first thing you want to pick out are the places where the graph crosses or bounces off the x-axis, because those are your zeros or your roots, okay? So I can see that I have a 0 at -4. 1, 2, 3, 4. And then I'm going to have to approximate this one a little bit. I have no choice because I don't have an equation, so I have to just look at it off the graph. So it's okay to make some assumptions when looking at graphs, and I'm going to just assume that's at -1/2. And then 1, 2, 3. And then that last one is at x equals 3, but that one counts twice. And the way that we know that it counts twice is because when you look at the graph bounces off the x-axis right there. It looks like a parabola, like a second degree. It has a turning point there. For all of those reasons, we know that this particular 0 of 3 will count twice. So that will help us when we're making our equation. I also noticed that this graph has a y-intercept of 2. And it has even degree and behavior, because both of the arrows point in the same direction on both the left side and the right side of the graph. So because they're both pointing up, I know my degree will be even. So it makes sense to have 1, 2, 3, 4 zeros, because if my degree is even, I need an even number of zeros. Okay, so first I'm going to get to work converting the zeros into factors, just like we did in our previous example. So I have 1 0 of -4. So in order for there to be a 0 of -4, there must have been a factor, right? A factor of x plus 4. So that's one of my factors. And then in order for there to be a 0 of -1/2, and this is a special one because it has a fraction, right? So I'll have to multiply by the denominator. That's back to this step right here. To remove the fractions, we multiply by the denominator. And then that gives me 2x equals -1. But then to get all the way to the factor that was equal to 0, I add the 1 back. So in order to have a 0 of -1/2, I must have had a factor of 2x plus 1. And then my last factor was 3, or my last 0 was 3. So in order to have a 0 of 3, I must have had a factor of x minus 3. And again, this one counts twice. So there's actually two factors of x minus 3. Okay, so here's what I have so far. So far I have y equals, and I'm going to put this a right here because I'm going to solve for that in a moment. Solve for a, because we cannot assume it equals 1 anymore because we have more information from looking at the graph to be able to determine a. And then I'm going to write my factor of x plus 4, my factor of 2x plus 1, and my 2 factors of x minus 3. And you can write that as x minus 3 squared as well. But I wanted to show here there's really 4 full factors, right? That's how I'm going to end up with that even degree. Both arrows pointing up with 4 factors. Okay, now, here's where I use the y-intercept. I'm going to plug in 2 for y, and I'm going to plug in 0 for every x. Because what the y-intercept is telling me is that according to this equation, whenever x is 0, so if I plug in 0 for all these x's, okay, so I plugged in 0 for every single x, 0, 0, 0, 0, and I plugged in 2 for y. Because according to this graph, if x is 0, y is 2. So what I can do is use that information to solve for a. So I get 2 is equal to a times 4 times 1 times -3 times -3 again. And then what that tells me is that 2 is equal to a times 4 times 1 times 9, which is 36, right? A is being multiplied by all these, and all these multiply together to be 36. And my job is to solve for a. So I'm going to divide both sides of this equation by 36. 2 divides evenly into 36 18 times. So my a value is a tiny fraction, 1 over 18. So that tells me my graph must have had a vertical shrink. Okay, in order to have such a small a value, that's what must have been the case with my equation. Okay, so then my final answer, final answer right here is, and I'll just leave it in intercept form, but instead of assuming a is 1, because a was not 1, clearly, I'm going to solve for a using the y-intercept and use that value as my leading coefficient. So it's 1 over 18 times my factor of x plus 4, my factor of 2x plus 1, and my 2 identical factors of x minus 3. This is my final answer for number 5. And you could FOIL all this out to get the standard form, but it would take a long time, and it's not really, there's no real reason to do that, right? This alone can help you see what the equation would be. And so I highly encourage you to go ahead and plug it in on Desmos. Check it on Desmos to see, and you can plug it in just like this in factored form and see, does it create a graph that kind of looks like this, right? And maybe play around with different a values. What would happen if we did assume a was 1? Would that give me the graph that looks like this? Would it have a y-intercept of 2? And see the importance of actually going back this time and solving for 1 over 18, because we have to write an equation that, if we checked it on Desmos, would match this graph, right? So maybe I'll make a special note here, because we didn't have to do this. When all I did was give you the zeros, I didn't require you to determine the a value. And so in all of those instances, back in examples 1 through 4, we were just assuming the a is 1. But now that we're given the graph and we can see the y-intercept and even other points on the graph, we now are able to find what a actually is. And so we should always, always find it when we're given a graph. And remember, a is that leading coefficient. It's that number that's out in front of all the factors, okay? And so there was our a value for this one. Okay, so let's go now we'll finish off with number 6, and we're going to do the same thing. We're going to start by identifying my zeros, which ones bounce, which ones touch, okay? And it's okay, again, to approximate what their values are, because all we can do is look at the graph and just try to get a possible equation to match that graph. So that possible is allowing us a little bit of wiggle room for approximating. So over here on the left, 1, 2, 3, 4, it looks like I have a 0 of x equals -4. That's going to count twice, since the graph bounced off the x-axis there and looks like a parabola. It looks like a second degree, a power of 2. So that's because it came from a factor that had a power of 2. And then now I know this looks like it's crossing somewhere between 1 and 2, but let's go ahead and just assume that it's crossing right at 2, or let's just go ahead and say that it's crossing at 2 to make it a little easier to get our final factor. Okay, so I have 2 zeros, but really 3 altogether if I count this one twice. So then I'm going to turn those zeros into factors. So if I add 4 back over, I get x plus 4 is 0. That means x plus 4 was my factor. And then with this x equals 2, 0, if I subtracted it back over, I'd get x minus 2, which is 0. So that x minus 2 must have been the factor. And there must be 2 factors of that in order to have it. Oh, no, that's the other one. Sorry, x minus 2 just crossed one time. It was x plus 4. There must be 2 factors of x plus 4, since that was the 0 that bounced off the x-axis. Okay, so then I start by writing my equation. I put a in front, okay, and then I count my factor of x plus 4 twice, because it bounced off the x-axis, and then I have a single factor of x minus 2, and then I'm going to use the y-intercept to solve for a. The y-intercept is right here, 1, 2, 3. It's at 0, 3. Couple comments though, sorry, couple quick comments before we do this. First thing, or not first thing, but one other thing to notice is that these ends are pointing in opposite directions, right? One is on the left side, it's going up, on the right side, it's going down. So I know that my degree should be odd. Another indicator that technically I should have an odd number of zeros. So that could help remind me that one of them needs to count twice in order for it to have arrows pointing in opposite directions. That's one thing. But also it's flip-flop from like a typical odd degree function. Typically odd degree functions look like this, right? They go up on the right and down on the left. But this is flip-flop, which tells me that my a value, my leading coefficient, my a value must be less than 0. It must be negative. So let's keep an eye out for that as I'm solving for it. I should end up with an a value that's less than 0. But I'll go ahead and plug in 3 for y and then 0 for both of my x's. So y equals 3 equals a times 0 plus 4 squared times 0 minus 2. I'm just subbing in 0 in place of x and 3 in place of y. And so then I get this. 3 is equal to a times 4 squared, which is 16 times negative 2. So then that gives me 3 is equal to negative 32a. And then to get a by itself, I will divide by negative 32. And so I get this. A is equal to negative 3 over 32. So it's also a small fraction like it was in number 5. So there must have been a vertical shrink and a vertical reflection in this particular graph. But that's what we expected, right? This looks about right because we were expecting our a to come out negative. So final answer for this one. Final answer is I will have my y equal to the a value of negative 3 over 32 times my 2 factors of x plus 4 times my linear factor of x minus 2. And again, I highly encourage you to check these on Desmos, and maybe I'll go ahead and do that now. So let's go ahead and take a look at So let's go ahead and do that right here. Let's go ahead and type in, let's see, we had negative 3 over 32 times x plus 4 squared, and then times x minus 2. And what do you know? Look at that. It looks just like that graph. How cool is that? It looks just like that graph. It's bouncing right here at negative 4 because we squared that. It's hitting the y-axis at 3 and hitting the x-axis at 2. And the arrows are pointing in opposite directions. I don't know about you, but I just think that's so cool that we can take a graph that looks complicated like this and come up with an equation that generates pretty much that same exact graph. So these are the final answers for 5 and 6, and I'll see you in class.